This is section 10.5 in your textbook, and the topic is completing the square. First, I want to ask you, how would you solve a problem that looks like this? We have the quantity x plus 2 squared equals 49. One thing that you might do is to take the square root of both sides of this equation. Remember, any operation that keeps an equation balanced doesn't change the solutions to that equation. So when we take the square root of both sides of this, on the left-hand side, we'll have the square root of the quantity x plus 2 squared, and on the right, the square root of 49. On the left-hand side, the square root and the squaring are inverse operations. They undo each other. So all we're left with on the left-hand side is x plus 2. On the right, we need to make sure that we have both the positive square root of 49 and the negative square root of 49. 7 times 7 is 49, but negative 7 times negative 7 is also 49. And we need to consider both the positive and the negative square roots when we're looking for values of x that are solutions to the original equation. Now, we could simply subtract 2 from both sides, and that would give us one equation that goes with the positive square root, and that would look like this. X plus 2 equals positive 7, so x would have to be 5. We would also look at the equation that goes with the negative square root. This would be x plus 2 equals negative 7, so x could be negative 9. Notice in the original equation at the top of this slide that if you plug in either 5 or negative 9 for x, and then square that quantity plus 2, you will in fact get 49. So there are two solutions to this equation. There are two numbers we can plug in for x that make the left and the right sides of the equation equal each other. So how would we solve a problem that looks a little bit different? On the left-hand side, now we have a polynomial. X squared plus 4x plus 4 equals 49. Well, one thing we might do is to notice that the expression on the left-hand side, x squared plus 4x plus 4, can be rewritten in factored form. This is a perfect square trinomial. We can factor it into x plus 2 times x plus 2 on the left-hand side, and then simply rewrite that as x plus 2, that whole quantity, squared, equals 49. Now we have the same problem that we did on the previous page. And we go through the same steps. We take the square root of both sides, and so on. Here's a slightly harder problem. X squared plus 4x plus 2 equals 47. The quantity on the left is not a perfect square, so we can't factor it into a perfect square and then simply take the square root of both sides of the equation. But here's what we can do. We can do a step that keeps our equation balanced, that is, it doesn't change the solutions to our equation, but that will turn the left-hand side into a perfect square. If I add 2 to both sides of this equation, that keeps the equation balanced, so it doesn't change the solutions. And when I do that, I get x squared plus 4x plus 4 equals 49. Now this is the same problem as we had on the previous slide. The left-hand side now is a perfect square. I can rewrite it in its factored form, x plus 2, that whole quantity squared, equals 49, and I can take the square root of both sides and proceed as we did in the previous two slides. This process of adding something, in this case it was 2, to make the left-hand side be a perfect square, we call it completing the square. We add a little bit to make the left-hand side become a perfect square trinomial. Here are the steps to completing the square. We start off with a polynomial that is not a perfect square. An example is x squared plus 8x plus 2 equals 11. Then we're going to add or subtract a number to make the left-hand side, that polynomial in this case, into a perfect square. We don't need to worry about whether or not the right-hand side ends up as a perfect square. Sometimes it will, and sometimes it won't. The only thing we need to make into a perfect square is the polynomial. So in this case, I'm going to add 14 to both sides. That makes the left-hand side of this equation be x squared plus 8x plus 16. That is a perfect square. That is x plus 4, that quantity, squared. I had to add 14 to the right-hand side to keep the equation balanced, and it happened to be that I ended up with a perfect square on the right-hand side as well. Once I do that, I can take the square root of both sides of the equation, and I get, in this case, x plus 4 equals positive or negative 5. And when I solve those two equations, x plus 4 equals positive 5 and x plus 4 equals negative 5, I get the two solutions to this equation, either x equals 1 or x equals negative 9. So how do you decide what to add? What needs to go in the blank to make the trinomial shown below be a perfect square? I have x squared plus 6x plus something, and I need to know what goes in place of that something. What I want to do is to factor this so that it becomes x plus something, that whole quantity, squared. And I need to know what should replace the question mark. Well, let's think of it using our box method. In the top left box, we're going to have x squared. And I know that the two boxes in opposite corners need to add up to 6x. And since this is going to be a perfect square, I know that the things in the opposite corners need to be equal to each other. Those two things that add up to 6x, they have to equal each other. And I'm not sure what goes in that box down below. That's my question mark. I need to find out what needs to go in the bottom right-hand box. Well, let's see. I know that on the factors in the outside, I'll need an x and an x to make my x squared term. I know that the two boxes in opposite corners are going to need to add up to 6x, and they need to be equal to each other. So it must be that each of them is 3x. I take that 6x and divide it in half. Half goes in each of those two boxes. So it must be that the remaining factors around the outside are 3 and 3. So what I'm going to factor this expression into is x plus 3 times x plus 3, or the quantity x plus 3 squared. So what goes in place of the question mark down below? Well, it looks like we need to replace that with a 9. So this expression, when we complete the square, we add a 9 to it. A 9 goes in place of the question mark, and then it factors into x plus 3, that whole quantity, squared. A reasonable question to ask at this point is, how do you decide what to add? In the previous problem, we knew that what needed to go in place of the question mark was the number 9, but how can we figure that out in general? Well, if the first part of our polynomial looks like this, x squared plus bx, or b is some number, and I want to know, what do I need to add to this to make it a perfect square trinomial? Here's a rule of thumb that'll help. You want to take that number b and cut it in half, that's b over 2, and then take whatever you get then and square it. So what you want to add is b over 2 squared. That's the thing you add to make it into a perfect square trinomial. Let's look at an example for this that has numbers. Before we do, it's important to notice in this case that there's no coefficient on the x squared. Actually, there is a coefficient there. It's the number 1. We don't usually write it. But what we have is a plain old x squared at the front. Adding b over 2 squared only works when there's no coefficient on that x squared term. So let's look at this with a number that'll make it a little easier. Here's an example. If I start with x squared plus 10x, and I want to know what do I have to add to this to make it a perfect square trinomial. I'm going to take 10 and divide it in half. That's 5. And then I'll take that and square it. So I'm going to have to add 25 to make this a perfect square. When I factor it then, it's going to factor into x plus 10 over 2, also known as 5, squared. Let's see if we can find a pattern using a box of what to add. Here's an example of a problem we could solve by completing the square. X squared minus 16x equals negative 15. So the first step that we could do is we could recognize we're going to make some blank spaces. Okay? And this is going to be what we add to both sides to make the left-hand side of this equation be a perfect square trinomial. So the question is, what goes in those blanks? I want this to factor into x minus something squared, and I need to know what that something should be. So here's how the boxes can help. Let's focus on the left-hand side of our equation, the x squared minus 16x plus something. We'll put the x squared here. We know that the two boxes across from each other, the boxes on the diagonal, have to add up to negative 16x. And we're trying to find out what goes in the bottom right-hand box. That negative 16x is going to get split in half between the two boxes in the corners. This is the b over 2 part. So I know in my factoring that I'm going to need to have negative 8x and negative 8x. I take that negative 16x and I split it exactly in half, and half of it goes in each of those two boxes. Once I do that, I know that the factors around the outside need to be x and negative 8 and x and negative 8. And so the bottom right-hand corner, this needs to be 64, because negative 8 times negative 8 gives me positive 64. That's how I decide what to add to both sides. I'm adding 64 to both sides. When I factor the left-hand side then, it factors into x minus 8, the whole thing squared. And on the right-hand side, I have negative 15 plus 64. The plus 64 is what I added to keep my equation balanced. When I simplify the right-hand side of this, negative 15 plus 64 gives me 49. So now I have this expression, x minus 8, the quantity squared, equals 49. What do I do next? Well, now I have this expression, x minus 8, that quantity squared, equals 49. I'm going to take the square root of both sides, so I have x minus 8 on the left, and I have both the positive and negative square root of 49 on the right. So x minus 8 equals plus or minus 7. I can add 8 to both sides of my equation to get the x by itself, and so I have x equals 8 plus or minus 7. This is really two equations written, smushed together as one. So the solutions are x equals 8 plus 7, that's 15, and x equals 8 minus 7, that's 1. So x equals 15 and x equals 1 are the solutions to the equation. I can check those solutions in the original equation. This is the equation we started with. And I can plug in both of the solutions, and let's see if they work. So if I plug in 15 for x in the original equation, 15 squared minus 16 times 15, is that equal to negative 15? When I do this math, I see that this in fact does check. Plugging in 15 for x does make the equation balance. Let's see what happens if I plug in x equals 1. When I replace the x in the original equation with 1, I get 1 squared minus 16 times 1. Does that equal negative 15? It does, in fact. The left-hand side becomes 1 minus 16, which is negative 15. So both x equals 15 and x equals 1 make my original equation balance. Let's go through another example. In this case, what's different is that when we begin, the coefficient on the x squared is 2, and we said we need for that coefficient to be 1. We need just a plain old x squared there. So the first thing that I'm going to do here, I'm going to start with my original equation, and I'm going to go through and I'm going to add 8 to each side. This gives me like a blank for the space that I'm going to do the completing the square part. Okay? That just gives me some space to complete the square. Now before I do anything else, I'm going to divide everything on the left and everything on the right by 2. That gets rid of that leading coefficient. It gives me x squared plus 10x equals 4. Now I've gotten rid of that coefficient on the x squared term, so I can proceed. What do I add to both sides to make the left-hand side be a perfect square trinomial? Well, I add b over 2 squared. b is 10, so b over 2, 10 over 2 is 5. And when I square that, I get 25. So I'm going to add 25 to each side. Now, the stuff on the left is a perfect square. The stuff on the left factors into x plus 5, that quantity squared. And on the right, I have 4 plus 25. Next, I'm going to take the square root of both sides of my equation. So I get x plus 5 equals positive or negative the square root of 29. Now notice that in this case, the square root of 29 is not going to come out to an integer. The square root of 29 is an irrational number. It's going to be somewhere between 5 and 6, and that's okay. I don't have to have the square root of a perfect square on the right-hand side for this process to work. The next step that I'm going to take is I'm going to subtract 5 from both sides of the equation to get the x by itself. So I have negative 5 plus or minus the square root of 29. This is going to give us two different values for x, depending on whether I do negative 5 plus the square root of 29 or negative 5 minus the square root of 29. So negative 5 plus the square root of 29 is approximately 0.39. And negative 5 minus the square root of 29 is approximately negative 10.39. So those are the two solutions. Either x can be 0.39 or x can be negative 10.39. They'll both make my original equation balance. I know that this process of completing the square looks kind of confusing, so let's go through another example together. Let's say that I start with the equation 3g squared minus 24g plus 27 equals 0. I'm going to start with my original equation, and I'm going to subtract 27 from each side and leave a blank for where I'm going to complete the square. Now, I notice that I have a leading coefficient of 3. The coefficient in front of the g squared term is 3, and I need for that coefficient to be a 1. So I'm going to divide everything on both sides of the equation by 3. When I do that, I get g squared minus 8g plus whatever I need to put in the blank equals negative 9. I'm going to use a box to help me figure out what goes in the blank. Let's focus on the left-hand side of the equation. I know that the g squared goes in the top left box here, and the minus 8g has to be evenly split between the two corner boxes. Negative 8g has to be evenly split between those. And I'm trying to figure out what has to go in the bottom right-hand corner. Well, if the negative 8g gets evenly split between those two boxes, it must be that negative 4g goes in each box. And so when I factor this expression, I'd have g minus 4 across the top, g minus 4 down the side. That means that we must be replacing the question mark in this box model with negative 4 times negative 4, which is positive 16. So 16 is what needs to go in the blank there. 16 is what I'm going to need to add to both sides of the equation to make the left side be a perfect square. So now I know that what I need to add to both sides is 16. That's what I found using my box method. And so I add 16 to both sides of this equation. Next, I'm going to factor the left-hand side as the square of a binomial. So it becomes g minus 4, the whole thing squared. And 16 plus negative 9 gives us 7. Now I'll take the square root of each side. On the left-hand side, I'll just have g minus 4. And on the right-hand side, I'll have plus or minus the square root of 7. The square root of 7 is an irrational number. I could estimate it with a decimal, but for now, I'm just going to leave it as the square root of 7. Next, I'm going to add 4 to both sides. And when I do that, I get g equals 4 plus or minus the square root of 7. So the solutions to the equation are 4 plus the square root of 7 and 4 minus the square root of 7. Unless I ask you to turn these into their decimal approximations, it's okay to leave them in this form. Now I want you to try, and I'll walk you through some steps as to how to solve this equation using completing the square. The equation we're working with is x squared minus 2x equals 3. So the first step that you need to do, you start out with your original equation, and you need to rewrite it with a blank where you're going to add in whatever you need to complete the square. And you're going to add the same thing to both sides to keep your equation balanced. So show those two blanks there. Now, you can use the box method to figure out what needs to go in those blanks. So let's focus on the left-hand side. You need for the top left box to be x squared, and you need the two boxes in opposite corners to be minus 2x. And you're trying to figure out what replaces the question mark here. So pause the presentation while you figure out what goes in place of the question mark. Now you've figured out what you think goes in place of the question mark in your box there, and you're going to add that to both sides of your equation. Then you're going to look at the left side of the equation, and you're going to write it in its factored form. Look at the box that you've created, and look at what you have x and x around the outside to find out what the factored form of the left side of your equation is. Then you're going to add the stuff on the right-hand side together. And I'm not going to tell you what's supposed to go in these blanks, so you need to be doing that on your own. So you'll have x minus whatever you decided goes there, squared, equals some number that's on the right-hand side. Then you're going to take the square root of both sides, so you'll have x minus whatever equals plus or minus the square root of whatever number you found on the right-hand side. And then you're going to add the same thing to both sides to get the x all by itself. So then you should end up with x equals some number plus or minus some other number. And if you've done all of this right, what you should get there is x equals 1 minus 2 and x equals 1 plus 2. So your solutions are -1 and +3. If you didn't get these two as the solutions, please go back and try this again, following through the steps that I've showed you. Once you're done, you can check those two solutions in the original equation. Let's plug in the solutions we got where x equals -1. Let's plug that into our original equation. If I replace the x's with -1, the equation does in fact check. -1 squared minus 2 times -1, that becomes 1 plus 2, and that does in fact equal 3. I can also plug in 3 in the original equation. 3 squared minus 2 times 3. Well, 3 squared is 9, and 2 times 3 is 6, and 9 minus 6 is indeed 3. So this one checks as well.